Welcome everyone to this CMCC webinar. Maybe we can wait 1 minute before we start, or in the meanwhile I can start with an introduction. Today's seminar is given by Dario Nicolì. I will present Dario soon after, and the topic is Decadal Predictability of European Precipitation, Insights from the Decadal Climate Prediction Project. First, a few words about CMCC itself. So CMCC is a global scientific institution focused on the study and modeling of climate change and its effects on society, with the mission seen here on the right-hand side. The new structure of CMCC includes 3 research institutes: Institute for Earth System Predictions, the Institute for Climate Resilience, and European Institute on Economics and Environment. A few words about the CMCC Supercomputing Center, which since 2008 has been the most powerful computational facility in Italy and among the most advanced in Europe, fully dedicated to climate change research, with the specifications that you see here on this slide. CMCC has offices at different places across the country. We are based here in Bologna. And I should mention that also CMCC has links and direct relationship with a number of academic institutions, universities, and research institutes across the country. Moving to the webinar, I should mention also that this will be recorded, and the link to the recording will be shared soon after. During the presentation, your audio and video are deactivated by default, so we kindly ask you to raise your questions through the question and answer section, or by raising your hand at the end of the presentation, and the moderator will give you the floor. And now I will ask you, Dario, to share your slides, please. I will stop sharing my screen. And I will say a few words about Dario himself. Dario started his studies in the Sapienza University of Rome, where he did his bachelor's on environmental engineering. And then he continued with the master's at the same university. During that, he spent his internship also at Woods Hole Oceanographic Institute in the US. Then he continued, he joined the PhD program of the Ca' Foscari University of Venice and CMCC Foundation here in Bologna. And he conducted his PhD research on global climate impacts of the Atlantic multidecadal variability. Ever since, in the last 6 years, Dario has been a postdoc conducting research at CMCC in the climate variability and predictions division, and he's the driving force behind our simulations. He has run the decadal predictions for DCPP, the CMCC contribution to DCPP in CMIP6, thus contributing to big European projects such as Blue Action, EUCP, and Aspect. Dario has already about 15 publications and counting. In fact, some of the results presented today have just been submitted for publication. Dario, I think I will pass the floor to you at this point.
Thank you, Panos. Good morning to everyone. So before to start, let me mention that today I'm going to present some relevant works in which I was and I am currently involved. Someone as principal investigator, other as collaborator, other performing the simulation, as is also Panos rightly mentioned for the DCPP. So let me briefly introduce the near-term predictability, which relies on the assumption that the coupled climate system and its component have elements, interaction, responses, which are predictable on internal and two decadal timescales. On the right side, we have a sketch provided by Kushner et al. In 2019, which are where there are drawn the internal and external sources of near-term predictability. In red, we have the ones related to the initialization, such as the ocean heat, salinity and carbon uptake, land use and snow cover and sea ice. But also in yellow, we have the natural forced source of predictability, such as the solar variability and also the volcanic aerosol. But we have also the emission and the aerosols given by the anthropogenic origin. So what is important to focus on the right sketch is that the near-term predictability problem lies in the confluence between initial value problem and forced boundary value problem. And for this reason, there is this project, which is the CMCC Decadal Climate Prediction Project. Is a coordinating multimodal investigation into decadal climate prediction, predictability, and variability. It is composed by 3 different shades. The first one, the component A, is devoted to the analysis and the production of the retrospective forecast, in also to better understand the historical decadal prediction skill. The second one is the B component, which substantially regards the analysis of the multimodal forecast. And but I want to start with the C component, which involves a number of case studies which are particularly interesting. For instance, to understand the climate shift and variation, both natural and naturally forced, such as respectively the AMV on volcanoes case. And I want to start with the AMV, and let me briefly introduce the AMV, which is the Atlantic Multi-Decadal Variability, which is a climate mode characterized by long-term variability of the North Atlantic sea surface temperature. And this variation has occurred on time scale of several decades. And in fact, we have to consider that the AMV affect the climate not only in the North Atlantic, but also beyond the North Atlantic Ocean. So on the right, we have an example of the AMV-related teleconnection occurred during boreal summer, such as the increase of Mediterranean sea surface temperature and Sahel precipitation, but also some remote impact, as the increase of precipitation over Siberia and the Indian region. So the first experimental protocol that we are going to examine is the twin experiment of AMV positive and AMV negative. So the imprint of the AMV is investigating using a novel experimental framework in which we are going to restore the North Atlantic sea surface temperature in order to simulate the positive and negative phase of the AMV. On the left, we have a sketch of the protocol. So to simulate the positive phase, we are going to superimpose on the model climatology one standard deviation of the anomalous AMV SST pattern. In this way, we are going to simulate the positive phase of the AMV. To simulate the negative one, we substantially follow the same protocol, but this time we are going to subtract this anomalous AMV pattern. The difference between the AMV positive and AMV negative give us some hints regarding the AMV effect upon climate. Within the CMCC, I have run this simulation during my PhD. And in particular, I have used a fully coupled model in its standard resolution, so 1 degree per 1 degree in all the components. We have used 32 members for each phase, and each simulation was 10 years long. It's important to highlight that all this experiment has been conducted under preindustrial external forcing in order to isolate the effect of of the internal variability of the North Atlantic Ocean. Oh, sorry. So here it is an example of the from Nicolì et al. 2020, in which we have analyzed the summary response. So the results that we are going to see is the AMV positive minus AMV negative. On the left side, we can see the total precipitation field, the anomalous total precipitation field, and we can easily recognize over the European continent this dry-wet dipole, drier condition over the Mediterranean and wetter condition over Northern Europe, in agreement with previous results. We also find the same covariability of the AMV and precipitation found in Sun et al. 2015. To better understand the mechanism behind the results, to better understand the mechanism, we have analyzed the 300 hectopascal cryopotential heights. In particular, the middle panel shows the departure from the zonal mean. We can see that the imposed AMV pattern induces this east-west northern hemispheric wave train, which alters the upper tropospheric circulation over the entire northern region. Moreover, we have also analyzed the westerly flux, the effect of this westerly flux, which carries moisture from the North Atlantic, and this is partially responsible for the rainfall anomalies covering Europe. Regarding the winter response, I want to show you these results in a paper provided by Paolo Ruggeri et al. In 2021. We have used the same experimental protocol to analyze the winter response of the AMV. On the left, we can see the multimodal analysis of the Z500. In particular, we can recognize the weakening of the Lucian law over the North Pacific, and also this wave train which extends from the Pacific to the Nordic Seas, again altering the water circulation and showing also a La Niña-like response. To better understand, now I'm going to refer to a single model study conducted with our simulation. So on the left, we can see the 500 hectopascal zonal wind in shading, which shows the southward displacement of the North Atlantic jet. This is consistent also with the decrease of head heat transport highlighted by the purple contours between 60 degrees west and 30 degrees west. Regarding precipitation, shows in the lower panel, we can see that we found increased precipitation over Central and Southern Europe with a bright signal covering the Scandinavian regions. The lack of convergent structure highlighted by the contour in which is the velocity potential at 8500 hectopascal level suggests that this rainfall shift occurred over Europe could be associated with a displacement of the head-driven jet, and also associated to extra transport of moist air along the North Atlantic jet path. I have to mention that this study is limited by the single model approach, and the further investigation needs to better clarify the mechanism behind these results. Another interesting set of simulation is devoted to investigate the effect on volcanoes on past and potentially on future decadal prediction. In fact, previous studies have highlighted that volcanoes eruption can impact the AMV and by the direct surface cooling. So this protocol wants to investigate using a retrospective prediction, which is a forecast simply initialized in the past. So we repeat this retrospective prediction just before the last three major volcanic eruption, but this time we are going to delete the volcanic forcing effect. In this way, we have a prediction with the volcanic forcing and a prediction without the volcanic forcing. The difference among them allows us to disentangle the simulated volcanic effect over the climate. On the right, we are the three case studies prescribed by the DCPP C component. The Agung, the eruption of the Agung occurred in 1963, El Chichon occurred in 1982, and the Pinatubo occurred in June 1991. Regarding the Pinatubo, it's interesting to note that the volcanic forcing is fundamental to reproduce the observed sea surface temperature variability over the North Atlantic Ocean, which has followed the 19 and 91 eruption of Pinatubo. In fact, looking at the plot, we can see the upper panel, the prediction from several models. We are looking at a paper provided by Bilbao et al. This year, and we can see that the models are able to replicate the drop of temperature in the North Atlantic occurred during 19 and 1992. While in the lower panel, the experiment without the volcanic forcing, the prediction are not able to reproduce this drop of temperature. Another interesting aspect of this study is that after the first year of after the eruption, during the first year after the eruption, there is a general cooling which regards the tropics and the subtropics, but there is also a warming in the Eurasian Arctic sector, in particular over the Barents and Barents Sea, probably due to the fact that the general cooling is going to accelerate the Atlantic meridional returning circulation, and so transporting more warm water toward the Arctic. Now we are going to explore the A component, which, as already said, regards the retrospective forecast. They are used especially to understand the decadal prediction system skill. But what is a decadal prediction system? So here there is a sketch provided by Solaraju, Morali et al. In 2022. We can see in black the observed Athanasiadis of the observed variable, for instance, could be 2 meter temperature, and we can see in gray the historical simulation, and in brownish the scenario simulation. We can see that the historical simulation in blue has been initialized in 1850 and then is free to evolve under the historical and then scenario forcing. On the other hand, the decadal prediction has been initialized every year, starting from 1960 to nowadays. Here there are sketches just for initialization, but we have to think that we initialize the system every year. On the right, just a bit of vocabulary to better understand next slides. When we talk about the forecast year 1, we refer to the mean of the first year after each simulation. Forecast year 5 means the 5th year, and forecast year 1 to 10 means that we analyze the 10-year mean of the forecast. Here now I'm going to present work just submitted to Environmental Research Letter regarding the wintertime European precipitation. In this work, we have collected 7 different CMCC models, joining both to the decadal prediction and to the historical and climate projection efforts. In particular, we are considering the climatology of the period 1980-2010, and the horizontal resolution of this model spans from 2 degrees to half of degree. It's important also to say that these two grand ensembles share the same CMCC external forcing. So historical forcing from 1960 to 2014 and scenario forcing from 2015 onwards. According to the protocol, the chosen scenario is the RCP 4.5. The Decadal Prediction Ensemble, hereafter the init Grand Ensemble, includes 79 members, while the historical and projection considers 53 members. Now I show you one of the canonical metrics to evaluate the goodness of a system, which is the anomaly correlation coefficient, which is essentially a measure of the agreement between the observed anomalies and the simulated anomalies. The first row represents the surface temperature field as 2 meter temperature over land and sea surface temperature over ocean, while the lower row represents the precipitation field. On the left, we have the assessment of the ACC of the init Grand Ensemble, and if we focus our attention of the A plot, we can see that the Grand Ensemble, the initialized Grand Ensemble is able to capture the observed anomalies more or less over the entire domain, with the exception of a part of the North Atlantic current. While regarding the precipitation field, we can see that the Grand Ensemble is able to capture the anomalies, especially over Northern Europe and Northeastern Europe, but also over the Iberian Peninsula, northeast coast of Africa, and there are also significant ACC value also over Balkan Peninsula and Turkey. But what is more interesting is that the difference between the initialized and non-initialized Grand Ensemble. Focusing on surface temperature, we can see that we have enhanced scale covering the subpolar North Atlantic Ocean when we look at sea surface temperature difference. While regarding precipitation, we can see that we have increased scale covering the Mediterranean countries, so the Iberian Peninsula, again the northwestern coast of Africa, part also of Italy, and especially Turkey. So, starting from this, we have tried to better understand why we have these responses. Before to go on, it was to mention that what is the North Atlantic Oscillation? North Atlantic Oscillation is an atmospheric mode of variability given by the difference in mean sea level pressure anomalies over these two longitudinal bands, according to the definition of Jianping and Wong 2003. It is also characterized by several teleconnections, especially related to the European precipitation. In fact, during a positive phase of the AMV, we can see that there is a strengthening of the wind trades over the North Atlantic and a warm, dry Mediterranean and a wet, stormy Northern Europe. On the other side, during a negative phase of the of the NAO, we have a weakening of the trade wind and also a wetter Mediterranean. So, known this, we have decided to analyze the atmospheric circulation in ERA 5 dataset as a reference of the observed world. And we have found, without any surprise, this is a known fact in literature, that the first principal component over the Euro-Atlantic sector, when we consider 10-year mean and wintertime season, is the NAO index, which correlates with the first principal component at 0.99. So, starting from this premise, we have analyzed the NAO index in our grand ensembles. We have found that the Decadal prediction in red in the plot is able to replicate quite good the variability of the observed NAO index, correlating at 0.58. While the historical and projection given in blue, given by the blue curve in the plot, struggle to do so, correlating at 0.18. But it's important also to note that during the last part of the record, the blue curve is even as a sign even a sign reversed when we look at the NAO variability. So, summarizing, we have found that the Decadal prediction where they produce the NAO index, but also where they produce the observed subpolar North Atlantic sea surface temperature variability. So, we have used these two indices to build an hybrid model. In particular, we have used a linear regression to determine the empirical coefficient given by the observed relationship between the NAO index, subpolar North Atlantic sea surface temperature, and precipitation. So we apply this empirical coefficient to the model NAO index and subpolar North Atlantic sea surface temperature in order to depict the hybrid precipitation. On the right, we have the ACC that I shown before for the winter time and for forecast year 1 to 10. And then below, you can see the new hybrid forecast, the hybrid ACC for the precipitation. We can see that we gain there are high values of ACC, not only limited to the Mediterranean countries or to the Northern Europe, but also in south of France, part of central Italy. So we increase generally over the domain the ACC. We have to mention that the two indices, the NAO and the subpolar North Atlantic sea surface temperature, are not completely independent. And so we have to further investigate on this relationship. In fact, we have also an interesting work provided by Patrizio et al., which is going to submit to Nature Journal, in which they show that the correlation between NAO index and subpolar North Atlantic. In particular, if you focus your attention on the top left panel, we can see for different models joining to the DCPP effort, the ACC for the NAO index. We can see that the models that are able to capture the NAO index, which are the CMCC1, the large ensemble of CHESM, and the HADJAM1, are able also to capture the ACC for the trending sea surface temperature on the left. And this is important. But to better understand the mechanism behind this response, they have also analyzed the correlation between the atmospheric response during winter, so in this case the mean sea level pressure, and the subpolar sea surface temperature during the previous season, the autumn. So on the left, we have the response for the era 5, and we can see that those models that are able to capture the NAO and the SST in terms of ACC are able also to replicate the correlation between the mean sea level pressure in winter and mean sea level and the subpolar sea surface temperature in the previous season. And this is important because this is the first step to investigate the origin of the NAO index, which is still an open question in literature. Now I'm going to in the details of the last component, which is the big component regarding the quasi-real-time multimodal forecasts. In this case, I'm going to present our CMCC Decadal prediction system, which now we can happily say that we reach the ensemble size of 40 members, and so we can consider as a large ensemble. And in particular, our hindcast has been initialized every year, starting from 1960 to 2019, and we provide forecasts to the WMO for the WMO Decadal Climate Assessment every year, starting from 2020. We apply a full field initialization strategy, providing we can say a snapshot of each component to initialize our simulation, and this is an effort starting during the UCP project and is now continuing under the umbrella of the Aspect project. I'm not going into details in the model components, which are extensively evaluated and described in the evaluation paper, but I want to focus your attention, here we have an example of the evaluation skill of our large ensemble. I'm not going into details in all the variables for a matter of time, but I want to show you the one regarding the precipitation. For winter time, we have here we have the winter time precipitation ACC for the forecast year 1 to 10. We can see that highest value of ACC cover the Northern Europe as well as the Mediterranean country, with significant values again covering the Iberian Peninsula, northwest coast of Africa, and in general we increase the signal that we have already detected in the previous assessment of 20 members. When we compare this large ensemble to the historical, considering also the difference in ensemble size, since the historical has 10 members, we can see that we improve much the skill to the ability to predict the observed anomalies, especially over the northern part of Iberian Peninsula, central and southern Italy, Balkans, Turkey, and especially over northwest part of northwest coast of Africa. But also we can see that there is an increase of ACC values in covering the Scandinavian regions. Another matrix that I'm going to show you the goodness of our system to well predict precipitation is given below by the root mean square error ratio, which is simply the ratio between the root mean square error of decadal prediction and the root mean square error of historical and projection. So when you can see the red spot, this means that the values are less than 1, and this means that the root mean square error of decadal prediction is less than the one of historical and projection. And we can see that in red we have such improvement related not only to the Mediterranean countries, but also to the Scandinavian region, Scotland, and part of Northwest Europe. So now we are going to explore the next decade climate, which are a couple of slides. In particular, I'm going to show you last CMCC forecast issued in November 2023 in order to predict the climate of the period 2024-2033. On the left, we have the annual global surface temperature. In particular, we have the 2-meter temperature variable. The anomalies are related to the pre-industrial period in order to highlight the well-known threshold of 1.5 degrees Celsius. In fact, in blue, we have the ensemble mean of our forecast and of our hindcast, and then initialized in November 2023, we can see the annual mean of our forecast. We can see that our forecast has predicted the exceeding of this threshold for the year 2024 and also in the following years, for the majority of the ensemble members. This is consistent with communication provided by other institutes which join to the Aspect project. Now I'm going to show you the forecast for the next, the assessment of the anomalous precipitation for the next 10 years of winter time, during winter time. we have found this wet signal covering more or less the entire domain of Europe. But we have to consider what is interesting is the difference between the forecast and the projection. The differences, in fact, lie at the northern part of the domain and the southern part of the domain. So Scandinavian region, Scotland, but also Mediterranean countries. And we have to take into account that this is the skill of our system. So our system is better capture the anomalies over this region, which are the region where the anomalies difference between the forecast and projection. So finally, some future challenges and opportunities. We can say also recommendation for the next generation of Decadal prediction system. First, the Decadal prediction should benefit by increasing modeling resolution, especially to enhance physical processes representation, but also to reduce the bias related to the single models. It could be fine to work in order to address the signal to noise problem. Substantially, the model underestimates the predictable signal, for instance, of the NAO, and the large ensemble are needed to let emerge the signal, as also highlighted in Smith et al. 2020. Moreover, in light of the next assessment, it could be nice to use some statistical and artificial intelligence or machine learning methods to increase predictability and ensemble size, to meet also the need of stakeholders and policymakers, as done, for instance, in Dunston et al. 2022 or in Sassari et al. 2022. Another improvement that are required to the decadal prediction is related to initialization strategies. In fact, in particular, the full field initialization strategy cause a shock to the system, which deviate substantially our output toward the model apparatus. So we should work in order to minimize this shock, which is particularly relevant for the decadal prediction, as also highlighted in Porkova et al. 2023. Then I want to mention that the DCPP will contribute to the CNIP7 experiment, and in particular to the next phase of the IPCC record. This will include also the decadal predictions, the decadal climate predictions. Finally, it is important also to bridging the gaps, because the current climate universe, we can say, at now there are the seasonal prediction and decadal prediction, but there is a gap between them to cover the multi-annual variability, for instance. But there is also a gap between the decadal prediction and the projection, given the fact that the decadal prediction is limited by the 10th year of prediction, while the projection generally look at the end of the century or the half of the century. So these gaps need to be bridged, and the respective predictability should be explored. But today I'm happy to say that within the AFPET project we are bridging these gaps. In fact, several institutes, including ours, have developed a set of anchors to explore predictability at the extended seasonal, so 28 months time scale, but also beyond the 10th year, beyond the 10th year of prediction, so performing 20-year long simulation. In this way, we are trying to fill the gaps given by the seasonal prediction, the decadal prediction, and the projection. All these data are now openly downloadable. These data are openly and available on the SGF node, and in particular, the CMCC has contributed with 10 members for the extended seasonal and 10 members for the extended decadal timescales. Thank you.
Thank you very much, Dario, for this overview of all of your recent works. We are inviting participants to raise any questions if they have in the question and answers. For instance, there is a question. Thank you, Leon. I see your question. I will raise it to Dario. Leon Hermansson from Met Office is asking Dario, how are you planning on changing your initialization to reduce the shock in the AMOC? If we have such plans.
At now, I don't have such plans, but a possible way to reduce the shock of the Atlantic meridional Neptunian circulation could be to provide, for instance, analysis which the same, I would say that with the same model that with the same model, with a model which is consistent with the Decadal Prediction 1. In this way, we can try to reduce the bias related to the model itself. But this is an open question in literature, and also Yulia Polkova has discussed this shock in her paper.
We have plenty of time for discussion. In fact, thank you, Dario. There are also a couple of more questions. Arianna Trevisiol is asking, thank you, Dario, for the presentation. Can you explain in details the difference between the forecast and the projection? You mentioned in one of the last slides about precipitation. So can you explain the differences between the forecast and the projection in the last slides?
Yes.
And do you refer to general climate projection of the same model?
Yes, I'm going to take this slide. Okay. So I think that the Arianna refers to these plots. In particular, here there is the forecast is the one initialized with the condition on November 2023. So we provide the initial state of the climate system, and then we perform a 10-year long simulation under the scenario forcing, which are the RCP 4.5 scenario forcing. The projection share the same scenario, belongs to the same scenario forcing. So it's the projection related to 4.5 RCP 4.5, and it is conducted with the same models. But what is the difference? This projection comes from the historical simulation, because we have to take into account that the projection are the continuation of historical runs, and so has been so this simulation has been initialized in 1850, and then just free to evolve under the scenario forcing. The added value of the forecast is the fact that we provide at the beginning the initial state of the climate system. I hope I answered to Arianna.
Yes, Dario, thank you. There are more questions, so I move and I invite, of course, participants to come back and discuss this further with Dario, possibly via email. So another question comes from Adnan Abid, and I think Dario, Adnan refers to the slide that you presented from Kese's work. In this slide, you discussed autumn to winter relationship. What is the difference between full member and 10 members?
So, allora, sorry. On the left panel, on the scatter plot represent simply the ACC for the North Atlantic Oscillation Index. The difference between the full dots and the star is the fact that the full dots consider just 10 members of the ensemble, and this is done for a fair comparison among the ensemble sites of the different models. While the full ensemble for the CMCC, for instance, in this case was 20 members, but for the CHESM CAM5 joining to CMIP5 effort was 40 members. So in this case, it's interesting to note that our model with 20 members shows better skill in predicting the NAO compared to the 40 members of the NCAR CHES1 model. And
yes, indeed.
Okay.
I think you answered the question, Dario. We have also questions from our colleagues in Aspect. Freya from Met Office, Freya Gary is asking Dario, as many real-world use cases of climate information require not just skill of a variable, but to understand the extremes of a variable, do you have any plans to investigate how well extremes are captured in decadal prediction models?
That's an interesting question, thanks. Yes, the capture the stream in the decadal prediction is quite fundamental, but it's also quite demanding in terms of variables, because in general we need to have variables at daily timescales or even more refined in terms of time. But I think that there is some colleagues that is analyzing the extremes. I think Irini Sassari is working on this. Panos, correct me if I'm wrong. And but to me, it's still a field that deserves to be explored.
Indeed, Irini is working on that, and also colleagues from BSc. Carlos has looked at the extremes for precipitation and temperature in decadal predictions. Yes, this is interesting for the Aspect project, and we will discuss this with our colleagues. But I would like to raise some more questions to you, Dario. There is one question from Masami Nonaka from Jamstack in Japan. Thank you very much. The next decadal prediction is impressive. It suggests a sudden warming of global temperature in a few years and a hiatus after that. Is it related to ENSO or tropical Pacific decadal variability as in the 2000s?
That's a very interesting question. Thanks, Masami. And
maybe you can go back to that slide, Dario.
Yes. Okay. What is interesting, I think what is known is that the decadal prediction in general failed to reproduce the ENSO variability on decadal timescales. So we are able to capture the first 1 or 2 years, in best cases 2 years ENSO variability. But so probably the tropical Pacific decadal variability has a role in this outcome. By the way, this question could be addressed in the next assessment of the extended seasonal prediction, in which there could be some hints regarding this wet forecast. And
in fact, Dario,
here
in this plot, so we don't see the whole globe. But
Yeah.
we know that, and you mentioned that CMCC contributes also to the WMO lead center on multi-annual decadal predictions. And we can take this discussion further by looking at the global anomalies. Thank you very much, Masami. There are a couple more questions, and the next one is from Dorotea, Dario. Dorotea Iovino from CMCC. Thanks, Dario. Very comprehensive overview. The emphasis from the oceanic viewpoint often focuses on the AMOC. I agree with Leon that initialization is a key point to provide a consistent temperature salinity relationship. Anyway, if you mentioned it, sorry, I missed it. How is the AMOC variability reproduced in the CMCC runs?
So the AMOC variability, I don't have the plot here, but the AMOC variability in the CMCC runs is quite good for the first 5-6 years. So we have analyzed this during the thesis of Chiara Galeotti, in which I collaborate with her. I tutored her with other colleagues, and we have found that the AMOC variability, even if suffering of the initialization shock, is able to the system is able to well reproduce the first, as I said, 5-7 years of AMOC variability. But we are also to consider that we don't have a long-term observed record of the AMOC, so it's quite difficult also to assess really the skill of the system in terms of Atlantic meridional returning circulation.
Indeed, this is a difficulty, and we can discuss this further. We have more questions. Freya, there's another question from Freya Gary from that office. As we don't expect projections to be in sync, in phase, to say, in terms of internal variability, do you do any type of sensitivity analysis to look at how the ratio of skill in predicting in predictions versus projections might change if you apply a range of lags to the projections? If you take the projections and you consider changing, making a shift in the projections, possibly you get a better skill. I don't think we have analyzed this.
We don't have analyzed this. I know that there is a paper from the BSC group, I think Kos et al. 2022, if I remember well, that they constrain the projection to the decadal prediction in order to try to have a projection with I would say in phase internal variability, but to improve the projection outcome, I would say.
Yes, that's a very good answer, I think, Dario, and addresses this question. So there are methodologies to constrain projections, and of course one needs to choose which in which direction the projections should be constrained, considering interest in specific indices or variables and areas. Another question from Kyloch Biller. Thank you, Dario. Very nice and interesting presentation. I have more of a technical question. Considering the signal-to-noise paradox and the fact that the full ensemble is better in predicting the NAO, why don't you make the full ensemble available through ESGF? Then I think you have the answer to this, Dario.
Yes, our full ensemble is available actually on ESGF. The 40 members has been uploaded on ESGF, especially for the period, for the uncast period, so from 1960 to 2019. We are there are 20 members for the forecast, I think, but we are going to upload the others. But anyway, we have most 99% of our simulation are available on ESGF. Thank you.
And there are many more variables available for those interested. So get in contact with Dario if you would like to conduct analysis with variables that are not available at ESGF.
Sure. I'm
yes.
pleased to show you where you can find it.
So there are also positive comments, Dario, in the question and answers. Francesca Napoli is expressing thanks, and she says she will stay in touch for future developments. And Bina is asking a question from the University of Oxford, another colleague from Aspect Project. Thank you, Dario, for the great overview. Do you see any added value of winter precipitation skill or any other variable in the longer than 10-year initialized predictions you mentioned?
Okay. Yes, we have. I have just started to analyze our system. I completed the first analysis 2 days ago, more or less. And for sea surface temperature, it is shown that there is even more skill beyond the 10 years. This is because probably we are going to capture the multi-decadal variability, and that's all. So for the SST, we are sure that there is some skill, but for precipitation, we are still investigating.
Indeed, yes. And this analysis will be multi-model and multi-system analysis, Bina, with results will be shared, let's say, in spring as we move forward. I think these were the questions raised by the many participants, and we thank everybody for attending this webinar. I don't see any raised hands, and maybe we can. We are coming to the end of this seminar. Thank you, Dario, for this very interesting presentation. Even myself, I have some questions for you. We can discuss them next. Thank everybody for attending once again, and we will share the link to the recording. Thank you very much.
Thank you to everybody.